Welcome! Today we'll understand the max path score problem solved using dynamic programming in a grid. Here's the problem. Given a 2D grid and a value k, find a path from top left to bottom right, moving only right or down, that maximizes the score. The score increases when you step on cells with value 1 or 2, and k limits how many such non-zero cells you can step on. Let's take a small 3 by 3 example grid. The values can be 0, 1 or 2. We'll use k equals 3 for our example. The recursive function f of ij, k returns the maximum score to reach cell ij with at most k non-zero cells allowed along the path. Base case. When we reach cell 0.0, if k is still non-negative, we return 0, meaning we arrived successfully. If k is negative, we return negative infinity, meaning this path is invalid. For each cell, we check its value. If the cell is 0, we simply take the max of coming from the left or from above without reducing k. If the cell value is 1 or 2, we add that value to the score and reduce k by 1. This is because stepping on a non-zero cell costs 1 unit of our budget k. We memoize results in a 3D DP array indexed by I, j, and k, so we don't recompute the same subproblems. Let's trace through our example grid step by step. We start from the bottom right corner and recurse backward to the top left. For cell 2.2 with value 1, we look at cell 2.1 and cell 1.2, reducing k by 1 and adding 1 to the score from each direction. The recursion builds a tree of calls. Each call branches into at most 2 subcalls, one going left and one going up. The DP table stores computed results, so each state is computed only once. This brings the time complexity down to O, often times m times k. Let me walk through the key parts of the code. The function maxPathScore initializes a 3D DP array filled with -1 and calls the recursive function. Inside function, first we check base cases. At cell 0.0, return 0 if k is non-negative, else negative infinity. If k is negative anywhere, return negative infinity. Then we check if dpijk is already computed. If not -1, we return the stored value. For cell value 0, recurse left and up without changing k. For value 1 or 2, recurse with k minus 1 and add the cell value to the result. Finally, we store the max of left and up in dpijk and return it. The main function returns -1 if the answer is negative infinity. Let's visualize the DP table being filled for our example. Watch as each cell gets computed from its dependencies. And that's the complete solution. The key insight is using 3 dimensions: row I, column j, and remaining budget k to capture all possible states. The DP memoization ensures we solve each state only once. Great job following along.